Let me quickly go through this. We need to talk about addressing subnetting, forwarding, packet format, and fragmentation and reassembly. IP address is globally unique. It's 32-bit. So if used very efficiently, you could have 4 billion IP addresses. 40 亿. However, it's not used that efficiently. So we actually do not have 4 billion hosts on the internet. We have much fewer. However, if you have more hosts, more than 4 billion or more than what we can accommodate, then many hosts would use private IP addresses. So we have 4 billion public IP addresses, but they are not used exhaustively, and they are not used they are not used efficiently. So if we have hosts that cannot be allocated a public IP address, a normal IP address, then we can use a private IP address. And there's a segment we will see next. There's a segment of address. There are several segments of IP addresses which are destined for private IP addresses. Okay, and it's hierarchical, consisting of network ID and host ID. And a router usually has more than one interface and one address, one IP address, more than one. And a host usually have one IP address, but could have more than one IP addresses. Okay. So a router would have many addresses. However, a host usually have one, but could have more. See, a host might have just one interface card, one Ethernet interface or one wireless LAN, but on that interface card, it could have many IP addresses. So that's called IP aliasing. IP aliasing, meaning that you have multiple IP addresses on the same interface card. Okay, here's an example of IP address. This one is in National Zhongzheng University, which is the second author, Professor Wang's university. And it's for sure in binary, but usually we would represent it in say 140.123.1.1. Okay, since IP address is a multi-byte data structure, it's a multi-byte data, and we have talked about this in chapter 1 and also in chapter 2 about the little endian and big endian in memory and in transit. Okay, if it's in the memory, stored in the memory, then you need to know it might be stored in the big endian or in the little endian. See, this is the IP address. Okay, and in the big endian, it's stored in this way. The high order byte is stored in the low order address. The high order byte in the low order address. This is the memory address, and the address increases. Okay, so it's a high address here. So what you do is that if it's big endian, you store the high order byte in the low address. The low order byte in the high address. That's big endian. But for little endian, you store the high order byte in the high address, low order byte in the low address. That's little endian. And whether it's big or little, it depends on the CPU's architecture. If it's Pentium, might not be the same as ARM. Okay, that's the order, by order in memory. How about in transit? Then in transit, you need to care about byte order and bit order, not just byte order. You now care about bit order too. And we have said that IP is big endian, meaning that you would transmit the high order byte first. High order byte first in IP is big endian, so you transmit the high order byte first and then the low order byte. How about within the byte, the bit order? The bit order within a byte, that's things cared by the link layer. The link layer, say Ethernet is little endian, so it says that the low order bit within a byte should be transmitted first. So you transmit for this byte, you transmit the low order bit first. So you'll be transmitting this way, in this direction, the low order bit first, and then the high order bit. If it's the big endian bit order, then it will start from high order bit. Okay. So it's here it's little endian starting from the low order bit within a byte. Okay. So we have mentioned this in chapter 1 and chapter 2, but we say it again here. And hopefully it's clear enough by now. Okay, the stateful IP address, class 4 IP address. And when they allocate the IP addresses space, they view them as class 4, meaning within this range, it's class A, and this class B, class C, and class D is reserved for multicast, and then class E is reserved. Okay, so and 140 is here, so we are in class B. Okay. Okay, the difference between class B and class A and C is the size of the network. So here in class B, the size of the network is you got 16 bits in the host number. So within a network, you can have 2 to the order of 16. That will be 65,000. A little bit over 65,000 hosts within a network for class B. However, for class A, we got few class A network, but each network is huge. It's huge, 2 to the order of 24, which is big. But for class C, we got many class C networks, but each will be small, which each will be 2 to the order of 8, which will be 256 hosts. Okay. However, is that important for class? Well, if you have class C, say every time you allocate a network space to an organization, you essentially create an entry in every router globally. So if there are billion, well, not billion, tens, hundreds of thousands of routers in the global internet. Then if you allocate a network, then each router, each of these hundreds of thousands of routers will need to create a new entry for that network. So that is a problem when we allocate class C. If we allocate class C, okay, this is a class C address to this organization, and then another class C address to that, and we allocate many class C, and each of the class C network would introduce a new entry in the backbone router, then it's bad. We would have too many routing entries in the router for the backbone routers. Okay, so what we want to do is that instead of breaking down the ideal class into class lists, so we want to have class lists. Here's a class list. See, too many class C and too many class C address, and so then there'll be too many routing entries in the backbone router. So what we can do is that to have class lists inter-domain routing, meaning the network portion of the address could be arbitrary length. See, I don't see. See, the network address does not need to be this long. It could be this, any length. So essentially, we forget about class, the ideal class, just a class list, and the network address does not need to be 8 bit, 16 bit, or 24 bit. No, it could be 20 bit, 21 bit, any length. Then you essentially break down you can. So if I want to allocate class C, usually they don't allocate class C to one organization. They will allocate consecutive class C networks, consecutive class C addresses. Say I allocate 16 class C, each will be 256 addresses, and I allocate 16 and consecutively to one organization. Then this allocation of 16 class C address would just introduce one routing entry to the backbone routers. Okay, instead of 16 entry to the backbone router, just one new entry to the backbone router. Then it would improve the scalability, meaning the number of routing table entry will be reduced. So what they do is that they try to allocate consecutive class C addresses to an ISP, for example. So right now they don't consider the idea of class A, B, C, D that seriously, but class D is still kept there. If you are unicast, if it's unicast, then you don't use class D. You would use class A, B, C. Okay, and if that's the network address, and for the host ID, if it's 0, then it means the network itself. If it's all ones, FFFF means all ones, then it's a broadcast address of the network. So if I have an address of 140.113.255.255, then this is a broadcast address within the network of 140.113. Okay, 140.113 stands for NCTU. And if I put this address of 140.113.255.255, then it means the packet should be broadcast on the entire NCTU network. So it's broadcast address of the network. However, we usually, it's called remote broadcasting. So it used to be a way of attack. Say I send a packet to the network with 140.113.255.55, and the router should forward the packet to the NCTU router, and then at NCTU router it would broadcast the packet to all the hosts at NCTU. Suppose at NCTU there are 20,000 hosts, then 20,000 hosts should receive the packet, right? By the definition here. But then it becomes a way of attack, DOS denial of service. I could send a remote broadcast packet like this to any host, to any network. Then it would explode there, explosion there. Then there'll be a serious problem. So right now, most routers do not support this kind of remote broadcast. They would support local broadcast. For example, I sent instead of I sent the destination MAC address would have all ones. 6 bytes will be all ones. Then it will be local broadcast, which is used in ARP request, right? But for remote broadcast, it's dangerous. It's like sending a bomb to a remote network. So it's usually not supported by the routers. Okay, and subnet. The idea of subnet, and I think I run out of time, and I need to stop here.